So today we will learn proof techniques, and which is a very important part in this course. So the slide is visible. Uh,
Yes,
Yes,
sir.
sir.
okay, okay. So there are different ways you can prove a certain statement or proposition. So one is called proof by induction, proof by contradiction, proof by contraposition, which means A implies B is equivalent to saying not B implies not A. That we already know from our discrete math class. There are some direct proofs, uh, proof by extremality. So we'll discuss all these things, and proof by algorithm. This last one is sometimes called proof by algorithm or proof by construction. So each of these category will be explored here uh, throughout this course. So one of the purpose of this course is to learn how to prove certain propositions about graphs. Say for example, just proof by induction. So there is a theorem. Every walk contains some path. So every UV walk, that means the walk that starts at vertex U and ends at vertex V, contains a UV path also. Okay, so if you recall, what is a walk? So walk is basically you can choose any set of, you can choose a sequence of vertices. Uh, the only thing is they have to maintain the so between any two consecutive vertices there should be some edge. Okay, and when we are talking about UV path means no vertex and no edge is being repeated. Okay, so here it is, if you take any graph, if you construct any UV walk, it must contain some path. So this can prove by induction. So by induction on the length L of a UV walk W. So we prove it by induction. So induction parameter क्या होगा? Induction parameter होगा length of the walk, length of the UV walk. So length of the UV walk here is L. Okay, and this walk is denoted by W. So basic step is L equal to 0. So if there is a UV walk and where L is 0, that means there is no edge. That means this walk W consists of a single vertex where U equal to V. And in that case, this vertex itself is a UV path of length 0. So it is trivially proved. Now, induction step says that, so this is our induction hypothesis, that for L equal to 0 we have proven, for L greater than equal to 1, now we have to study. So say the claim holds for all the walks of all the UV walks of length less than L. So our induction hypothesis says that if the length of the walk is less than L, if the length of the walk is less than L, in that case this claim held, this claim is valid. Now we have to prove it for the length equal to L. So now consider a UV walk W of length L. Now two cases may happen. ये L लेंथ के जो UV walk है यहाँ पे there W has no repeated vertex, so no vertex is repeated in this walk. If no vertex is repeated, it immediately means that no edge is repeated. That means the walk itself is a path. So W is not only walk, W also represent a path also. So if W doesn't have any repeated vertex, then its vertices and edges form the path itself, form the path. If W has a repeated vertex W, then what we can do, we delete edges and vertices between appearances of W leaving. Okay, so take this example. Okay, suppose say one, yeah, so in this graph 1 2 3 5 1 2 3 5 4 4 2 1. Okay, it is a UV walk of length L. Okay, now यहाँ पे कौन कौन सा वर्टिसेस आप देख रहे हो रिपीट हो रहा है. सपोज 1 2 3 5 1 2 3 5 4 1 2 3 5 4 then 4 then 2 then 1. ओके, तो बहुत वर्टेक्स रिपीट हो रहा है. सो यू चूज एनी वन ऑफ देम. सो यहाँ पे लिखा गया है कि W हैज ए रिपीटेड वर्टेक्स, मतलब एटलीस्ट वन वर्टेक्स इज रिपीटेड देयर. यहाँ पे तो मल्टीपल वर्टेक्स रिपीट हो रहा है. 1 रिपीट हो रहा है, 2 रिपीट हो रहा है, 4 रिपीट हो रहा है. Suppose we take 4. Okay, so basically the point here is जो वर्टेक्स रिपीट हो रहा है उसमें एक हटा दो. जैसे यहाँ पे 1 2 3 5 4 4 2 1, तो 4 4 रिपीट हो रहा है. सिर्फ एक 4 को नहीं हटाओगे, ये दो 4 के बीच में और भी जो वर्टेक्स है वो हटा दोगे. सो यू रिमूव इट अगेन. ये क्या किसी दूसरे का था आई थिंक. I take an example of a UV. For example, you take this example. So we are trying to explain this case. W has a repeated vertex W. So W has a repeated vertex W. It means that at least one vertex is repeated. It may so happen more than one vertex can also be repeated. Okay. So यहाँ पे 1 2 3 5 1 2 3 5 4 4 2. So this is the UV walk of length L. Now what this claim says, deleting edges and vertices between the appearances of W. तो जो चीज दो बार रिपीट हो रहा है, जैसे यहाँ पे 4 4 रिपीट हो रहा है, तो 1 2 3 5 4 4 2, यहाँ पे 4 4 रिपीट हो रहा है, तो तुम एक 4 को रखो, दूसरे 4 को हटा दो. यहाँ पे 2 रिपीट हो रहा है दो बार, तो तुम 1 2 को हटा दो, so you will get a path where no vertex and edge will be repeated. You will get a so basically what happens, it says that if a vertex V is repeated, oh shit, इसके लिए deleting edges and vertices between appearances of W, leaving only one copy of W gives a shorter UV walk W prime contained in W. By induction hypothesis, the W prime contains a UV path P, and this path P is contained in W. So what it tells here, so suppose this is the path 1 2 3 5 4 4 2. Suppose this is the UV walk of length L. Now any vertex that is repeated, any vertex, if no vertex is repeated, then then this UV walk itself is a path. Say for example, if I take 1 2 3 5 4, if I take 1 2 3 5 4 is a UV walk of length L, in that case since no vertex is repeated, this itself gives you a path. That is the case 1. Case 2 says if few vertex repeated in this walk, in that case I can delete say 4 4 is repeated, so in that case I can delete 1 4 delete 1 4 and I get this one. Now this walk has length less than L. Now by induction hypothesis, the claim holds for lengths of length less than L. That means इसका length less than L है, so it is a walk less than L. So induction hypothesis can be applied, and what induction hypothesis says, okay, UV walk has a UV path. A shorter UV walk has a UV path. ये जो shorter UV path delete 4 के बाद जो walk मिला, suppose I call it a W prime. So this W prime has a UV path, and this is got from this induction hypothesis. Okay, we move to the next one, then I think things will be more clear. So every closed odd walk contains an odd cycle. Okay, so first of all, so we know what is a walk. Walk is a sequence of vertices. We have to sequence of vertices and edges, and it is and when it will be a closed walk, when the first vertex equal to last vertex, and when it is an odd walk, when the length of the walk is odd, so number of edges is odd. So by induction on length L on closed walk, so the induction parameter is length L of the closed odd walk. So this is the induction parameter. So L equal to 1. So a closed walk of length 1 traverses a cycle of length 1. So it is trivially proved. जैसे यहाँ पे 4 to 4. This is a closed odd walk of length 1. Now it is a self loop, so it is a cycle also. So that is the base case. Induction step says that for L greater than equal to 1, we have to prove it. Now the induction hypothesis says, assume the claim is true for all closed odd walk of length less than L. So इसका मतलब यह है कि अगर कोई क्लोज्ड ऑड वॉक का लेंथ L से कम होगा, इन दैट केस इट मस्ट हैव ए ऑड साइकिल. मुझे अभी प्रूफ करना है अगर इसका लेंथ इक्वल टू L है, then also we find an odd cycle. So there are two cases here also. The first case is W has no repeated vertex other than the first and the last. In that case, it's very trivial because W itself forms a cycle of odd length. Okay. So if W doesn't have any repeated vertex other than the first and the last, in that case, it itself constitutes the cycle of odd length. Now, what may be the case? Okay, some vertex V may be repeated in W. Okay. If vertex V is repeated in W, then view this walk W as starting at V, break W into two VV walks. Okay, so let's go to this example. Say for this graph 2 3 5 4 2 4 4 2 2 3 5 4, then 4 repeated 2. This is a UV closed odd walk of length L. Okay, तो इसका लेंथ है 5. अगर आप देखोगे इसका लेंथ है 5. Now since 4 is repeated, the vertex 4 is repeated, we can break this closed odd walk into two walks. Which are those two walks? One is a 4 4 walk, another is 4 2 3 5 4 walk. Okay, so 2 3 5 4 4 2. Okay, so since 4 is repeated, we can break the closed walk into two smaller walks of opposite parity. One is the first walk is a 4 4 walk, and second walk is 2 3 5 4 2. Okay, so I should actually, it should be written like this. It should be broken like 4 2 P5 4. Now this is an odd walk, this is an even walk. The smaller odd walk has length less than L. The smaller odd walk is less than L. So from induction hypothesis, the smaller odd walk always have an odd cycle within it. So it's being proven. So here you repeat things like, if vertex V is repeated in W, view W as starting at V. Break W into two VV walks. Since W has odd length, then so basically इसको दो साइकिल में मैं ब्रेक कर सकता हूँ. वन साइकिल का लेंथ होगा और दूसरे साइकिल का लेंथ होगा, दूसरे वर्क का लेंथ होगा इवन, since the whole length is odd. Okay, so जो even length है we can ignore it, but the smaller odd work that I get, smaller odd VV work that I get, that's length must be less than L. So the odd one is shorter than W. So by the induction hypothesis, that shorter odd work have an odd cycle, and this cycle appears in W itself. So it is proven. Okay. तो टुडे मैं ये स्लाइड आप लोगों के साथ शेयर करूंगा, मैं जितना यहाँ पे डिस्कस करता हूँ। एक बार आप घर में देख लेना, यू लुक इनटू द बुक आल्सो, एंड एक बार देखोगे तब क्लियर हो जाएगा। नाउ वी कम बैक टू कट वर्टेक्स कट एज। सो वी नो दिस डेफिनेशन जस्ट। So if you look into here, that this C is a cut vertex, because if I delete this vertex, then it will create more than one component. Okay. Similarly, AD is a cut edge, because if I delete it, I get two different components. So the components of a graph G are its maximal connected subgraph. A component is non-trivial if it contains an edge. ओके, सो ये डेफिनेशन बहुत इंपॉर्टेंट है कि नॉन ट्रिवियल कंपोनेंट किसको बोलते हैं, इफ इट कंटेन्स एन एज। जैसे सपोज मैं एक ग्राफ ले लेता हूं, जैसे अगर मैं और इसके साथ साथ so, ये दोनों मिला के एक ग्राफ है, राइट? ये दोनों मिला के यहाँ पे ए बी सी है, सपोज दिस इज डी। ओके, नाउ दिस ए बी सी जो है, दिस इज ए नॉन ट्रिवियल कंपोनेंट बिकॉज देयर आर एटलीस्ट वन एज इनटू दिस कंपोनेंट। यहाँ पे तो 3 एज है, so it is a non-trivial component. However, this vertex is a component, definitely it's a component, but it is a trivial component because it is not connected to some edge. So this component is trivial because it doesn't have any edge. Okay, so cut edge or cut vertex of a graph is an edge or vertex whose deletion increases the number of components. Okay, तो अगर मैं C को डिलीट करता हूँ तो more than one component create होगा। Similarly, अगर मैं ADH को भी डिलीट करता हूँ तो ये भी more than one component create करेगा। So AD is a cut edge, C is a cut vertex. Now, so we started our discussion with proof concepts. That first we discussed proof by induction. Now we discuss proof by contraposition. Proof by contraposition. So an edge is a cut edge if and only if it belongs to no cycle. Okay, an edge is a cut edge if and only if it doesn't belong to any cycle. So यहाँ पे मैं दो प्रोपोजिशन में इसको डिवाइड कर लेता हूँ। द प्रोपोजिशन ए इज an edge UV is a cut edge which is denoted by E. The second proposition B is E does not belong to a cycle. Okay. So our objective is to prove A if and only if B. So if part में मैं क्या प्रूफ कर रहा हूँ, if B then A. So B implies A, we have to prove, and to prove it we can prove the other way around. We can prove not A implies not B. So what is my not A here? If A is an edge, E is a cut edge. So not A means E is not a cut edge. If E is not a cut edge, then from a graph H, if I delete E, it remains connected. H minus E remains connected since it is not a cut edge. There exists an UV path in the graph H minus E. Okay, this UV path along with the edge E constitute the cycle. Okay. So constitute the cycle. So what? So that is my not B. Not B is E belongs to a cycle. So I will repeat this proof. So here says the NH is a cut edge if it doesn't belong to a cycle. So my proposition A is a cut edge, and proposition B is E doesn't belong to a cycle. So I have to prove A if and only if B. So the first we will prove the if part. That is B implies A. You have to prove. इसका meaning ये है कि we can also prove not A or implies not B. So what is my not A? E is not a cut edge. If E is not a cut edge, then from that we can easily say that. So the definition of cut edge says if I delete that edge, it will create more than one component. Now, if E is not a cut edge, that means H minus E, H is a graph. If I delete E from it, it remains connected. It remains connected का मतलब यह है कि if you take any two vertices UV in this graph H, then there exists a path, UV path in this graph H minus E. Abhi, if there is a path H minus E, and if you add E to this path, then it will definitely create a cycle. This UV path along with the edge E constitute a cycle. So not B is E belongs to a cycle. Okay. So basically इसको मैं not B लिख सकता हूँ. Now we have to prove that A only if B. Okay. So that means if A then B. A implies B, we have to prove. A only if B means A implies B. So A implies B proof करना का मतलब ये है कि मुझे not B implies not A को भी proof कर सकता हूँ. So what is my not B? Not B says not B means E belongs to a cycle. Okay. Then we have to prove that if E belongs to a cycle, if I delete edge E, it is not a cut edge. E is not a cut edge in that case. So E belongs to a cycle. If E belongs to a cycle, choose any UV from that graph H. Since H is connected, H has a UV path P. So यहाँ पे अगर मैं देखूं तो मुझे प्रूफ करना है नॉट बी implies नॉट ए. So not B is E belongs to a cycle. And what is not A? Not A means E is not a cut edge. So E is not a cut edge means H minus E is a connected graph. Okay. H minus E is a connected graph means for all UV in H minus E, there is a path P between U and V. Okay. So these things are actually implied to each other. If I write not A, E is not a cartridge, इससे मैं directly लिख सकता हूँ for all UV belongs to H minus E, there is a path P between U and V. Now what I will do, choose any two UV and a path P between them. Okay, so suppose I choose this UV and any path between them. So maybe U24V, this is path, U2354V, this is another path. Okay. Case 1, P does not contain E. Okay. Say for example, this 35 is my E. Suppose this 35 is my E. So there are two cases possible. P does not, so suppose if I choose this path U24V and E is my 35, in that case P does not contain E, क्योंकि मेरा P है ये path U24V, इसमें 35 नहीं है, E नहीं है. So on deletion of this E, if I delete this one, on deletion of E, UV is still connected in H minus E. So this is my H minus E graph, यहाँ पे भी UV अभी connected है. On deletion of E, UV is still connected in H minus E through P. So this is my P. This was my case 1. Case 2 is P contains E. Suppose instead of choosing U24V as my path, I choose my path like this, U2354V. Now in this case, if this is my P, path P, in this path there is an edge which is basically E. P contains E. So now what I can do, if I delete E, I can construct an alternate path. So I can form another path from U to X at which U is connected to a cycle followed by alternate XY path and YV path and Y. See, basically, we start our discussion, E belongs to a cycle. So this 3, 5 belongs to this cycle. 3, 5, 4 to this cycle. Okay. Now we can prove that if I delete E, still this graph will be connected. Okay. That means E cannot be a cartridge. So if P contains E, P is my this path. If P contains E, what I can do, I can create an alternate path. How? Since this is a cycle, I can always find from U35 करके जब मैं लौट रहा हूँ तो ये एक जो साइकिल में है, इस साइकिल का कोई एक वर्टेक्स x रहेगा. So यहाँ पे x is my 2. So I can always form another path from U to x. यहाँ पे U to 2. 2 is my x here. Okay, 2 equal to x here. X at which U is connected to the cycle. So U is connected to this cycle, followed by an alternate XY path. So this is my Y, followed by this XY path, and then YV path, where Y is a vertex connected to V. Y is a vertex connected to V. So if I delete this one, I can still get an alternate path. So that is how we prove it. So basically, the proposition was, if it is a cartridge, it doesn't belong to a cycle. Okay. So हम लोग दोनों हिसाब से प्रूफ किए थे. एक बार हम लोगों ने कुछ प्रूफ किए कि if it is a cartridge, then it cannot it can't belong to a cycle, and we prove it through contraposition. So we prove that If it belongs to a cycle, it cannot be a cartridge. And the second one is the other way around. If it doesn't belong to a cycle, it cannot be a cartridge. So we prove that. So for both ends, what I'm trying to see, to prove A implies B as well as B implies A, to proving both the proposition, we actually use the proof by contraposition. So B implies A मैंने proof नहीं किया. Instead, we prove that not A implies not B. Similarly, A implies B. A implies B हम लोगों ने directly proof नहीं किया. हम लोगों ने proof किया not B implies not A. So ये सेमी प्रूफ था, इसको पहले लिखा गया था, उसके एक्सप्लेनेशन ऐसी है. ये सेमी प्रूफ है. So this proof is written in the book. So उसको पिछले थोड़ा सा ब्रेक करके लिखा गया है. So ये जो दो चीज है, this the same theorem. So this is the proof that I have written in my own way, and बुक में ये प्रूफ लिखा है. तो कुछ छोटा स्टेप जंप है यहाँ पे, तो मैं दोनों ही रख दिया हूँ. सेम ही चीज है, आपको जिसको पढ़ने में आसानी होगी वो आप पढ़ लेना. Now we have few more definition. Independent set. We know that what is the independent set? So it is a subset of vertices which are non-adjacent to, where all the vertices are non-adjacent to each other. And our objective is to find the largest. We have to find the independences of largest size. Okay, so of maximum size. So the independence number of a graph is the maximum size of an independent set of vertices. जैसे इसमें 2 and 5 they are independent vertex. So 2 and 5 constitute an independent set. Again 1, 3, 4 they constitute another independent set. But its independence number is 3 because the largest size independent set is 1, 3 and 4, whose size is 3. We know what is a bipartite graph. So a graph is bipartite if its vertex can be arranged in two different partites such that all the edges are all the edges exist across the partite. So there is no edge within a given partite. Okay. So this ABCD, यहाँ पे AC is in one partite and BD is in another partite. We can rearrange this left-hand graph in the form of the right-hand graph such that AC is one partite, BD is one partite, and all the edges are across the partites. And what is a complete bipartite graph or biclic? Where for every pair of vertices UV, where U belongs to partite A and V belongs to partite B, there is an UV edge between them. So a complete bipartite graph is, or biclic is a bipartite graph whose edge set consists of all pairs having a vertex from each of the two disjoint sets of vertices. Okay. And this biclic is represented, can be defined as K R comma S. So it is a complete bipartite graph where one partite set has size R, another partite set has size S. Okay. and that means the number of edges is r into s. So total number of edges and total number of vertices are r plus s. A graph is bipartite if and only if it has no odd cycle. So first we prove the only if part. So it means that if the graph is bipartite, we have to prove that it doesn't have any odd cycle. So consider that G is a bipartite graph. So every walk alternates between the two sets of bipartition. So every return to the original parted set happens after an even number of steps. Hence G cannot have a cycle. So basically what it says is this. If G is a bipartite graph, we know that from the definition it has two partites and all its edges are across the partite. So we have to prove that it doesn't have any odd cycle. So it says every walk, suppose you start a walk from this partite. You can start from any one partite. You go to this. So to create a cycle, first of all, to create a cycle, you have to come back to this. So if you start your walk from here, to create a cycle, you must come back to this partite itself, and not only that, you have to reach to this point, right? So to create a cycle, you have to come back to its starting partite, right? That is why I say every walk alternates between the two sets of bipartition. So कोई भी walk तुम चालू कर रहे हो, यहाँ से यहाँ जाएगा, फिर वापस आएगा, फिर जाएगा, फिर वापस आएगा. It's like that. So every walk alternates between two sets of bipartition. So every return to the original partite set. So when you go there, the next edge cannot be, since it is a bipartite graph, the next edge cannot be like this. So the next edge must be here. Again, from here also, the next edge cannot be here. It must be here. Now, in similar pattern, the next stage from here to here is here. So every walk alternates between the two sets of bipartition. So every return to its original partite, when I am coming to original partite, set happens after an even number of steps. So 1, 2, 3, 4. So when if at all there is a cycle, this will merge to this, and you will reach here after an even number of steps. If there is no cycle, no issues. यहाँ पे बोला कि if it is a bipartite graph, then it has no odd cycle. But that means even if it has, it may not have even cycle also. But if some cycle at all exists, that must be even cycle. Okay, and the reason is, when you come back to when you start from a given partite and you assume that vertex belong to some cycle, so you start a walk from that particular vertex, from that partite, and you alternate between the partites, and when you actually come back to the original vertex, you see that you traverse even number of edges. Okay. So if the graph is bipartite, it cannot have an odd cycle. Now we have proved the other way around. given a graph, if it doesn't have an odd cycle, then it is a bipartite graph. Okay. So next चीज जो बोला गया, that is very important. Okay. If says that G is a graph which doesn't have any odd cycle. So okay. So suppose G is a graph that doesn't have an odd cycle. And since it is a bipartite graph, it doesn't mean it is a connected graph. It may have multiple components also. Okay, suppose it has n non-trivial components. So what is a non-trivial component? Non-trivial component means each component has at least one edge. Okay. So suppose it has n non-trivial components, h1, h2 up to hn. To prove the graph G is bipartite, we have to prove that each non-trivial component is bipartite by constructing a bipartition of hi. Okay. So basically what it will do, let U be a vertex in any non-trivial component hi. तो मुझे हर एक non-trivial component को bipartite proof करना है. Suppose I took any hi as my non-trivial component and U is a vertex in that. Now for each V in that component hi, let Fv is the minimum length of a UV path in hi. Since hi is connected, Fv is defined for each V belongs to Vh. So we have taken an example here. Suppose this is a component, okay, and we choose D as a particular vertex. So here this D be a vertex in this non-trivial component. Okay, so Fd is 0. Okay, then Fa is shortest dA path. Shortest dA path is of length 1. Shortest DC path is length 1. Shortest DB path is length 2. D to C, C to B. Okay, or it may be D to A to B, whatever it might be. So F of B, so distance of B from D is 2. Now what it suggests, okay, all the odd numbers, all these odd numbers should be clubbed into one partition and all the even numbers is clubbed into the another partition to give you two different partitions. That means यहाँ पे odd किस के लिए आया, A and C के लिए odd आया है, तो A C को एक पार्टाइट में डाल दो, B and D के लिए ये लेंथ इवन आया है तो इसको और एक पार्टाइट में डाल दो. And this is how you create two partition. So I will repeat this statement. Let U be a vertex in a non-trivial component hi. Then for every vertex V in that hi, Fv denote the minimum length UV path in hi. Now since hi is a connected, Fb is defined for every V belongs to Vh. Now X is one partition is constructed as follows, where Fv is even. We choose all those V in hi where Fv is even and y is another vertex where we choose all the vertices v for which fv is odd. So an edge v prime within x or y would create a closed odd walk using a shortest UV path. The edge v reverse v prime, such an odd walk must contain an odd cycle, which contradicts our hypothesis. Hence, x and y are independent cycles. So what we see here कि जिन लेंथ इवन आ रहा है उसको एक पार्टेट में डाल दो, जो ऑड आ रहा है उसको दूसरे पार्टेट में डाल दो. नाउ वंस वी डू दिस वी क्रिएट द पार्टीशन. अभी हम लोग थ्रू कॉन्ट्रडिक्शन प्रूफ करेंगे कि ये एक्स पार्टाइट के अंदर कोई एज नहीं रह सकता या वाई पार्टाइट के अंदर कोई एज नहीं रह सकता. Suppose an edge v prime exists between either x partite or y partite. Suppose it exists. In that case, what happens? In that case, there will be a closed odd walk can be created. How it will be created? So, if there is an edge between AC, then D to A to C and C to D. This will create a closed odd walk. And this closed odd walk always create a odd cycle. Okay. So an edge v prime within x or y would create a closed odd walk using a shortest UV path. Then the edge v prime which is within x partite, and again the reverse uv prime path. Such an odd walk must contain an odd cycle which contradicts our hypothesis. Okay, so xy must be independent set. So ये चीज मैं और एक बार आपको डिस्कस करके बताता हूँ. तो हम लोगों ने प्रूफ क्या करना था? A graph is bipartite if and only if it has no odd cycle. हम लोगों ने पहले only if प्रूफ किया था. only if क्या प्रूफ किया था? If it is a bipartite graph, it cannot have an odd cycle. And that is very simple. We see that since it is a bipartite graph, we know that we can create two partite. Then we choose any vertex in a particular partite, and we know that every walk alternates between these two sets of bipartition. So to create a cycle, you have to come back to the original partite, and to return back to the original partite, you must have traversed even number of steps. So there is no chance of creating odd cycle. The if part, the proving of if part says, suppose you are given a graph. Suppose you are given a graph that doesn't have any odd cycle. Then you have to prove that that graph is bipartite. Try to understand the point. So what is given to you? You are given a graph and told that it doesn't have an odd cycle. Now your task is to create a bipartite graph out of it. So what you do first? Okay, the graph that is given to you, it may have multiple components, h1 to hn. For each hi, you create a bipartite component for it. For each hi, you want to create two partites as follows. Okay, you choose any random vertex in hi, suppose that is u, and you calculate the distance from u to all other vertices in hi. जिस vertex का distance even होगा, you will put them in a partite, and जिन vertex का distance odd होगा, उसको दूसरे पार्टाइट में। सो इवन डिस्टेंस वाले को एक पार्टाइट में और डिस्टेंस वाले को दूसरे पार्टाइट में तुम डाल दिया। पर once you do that, so that is how you create something. What you have to prove that it is a bipartite graph. तुम्हें बोलना है कि अगर तुम ऐसे पार्टाइट क्रिएट करते हो, इफ यू क्रिएट द पार्टाइट इन दिस फैशन, then there cannot be any edge within the partite. That is something you have to prove. So तुम यहां पे जैसे A and C को एक जगह में क्लब कर दिए बिकॉज देयर डिस्टेंस इज ऑड। B and D को एक साथ क्लब कर दिए बिकॉज एक पार्टाइट में रख दिए बिकॉज देयर डिस्टेंस इज इवन फ्रॉम D. नाउ यू हैव टू प्रूव दैट कि ये जो पार्टाइट है विद इन दिस पार्टाइट ए सी या डीबी के अंदर कोई एज नहीं है। दैट इज यू हैव टू प्रूव। इफ यू प्रूव दैट, तुमने दो पार्टाइट तो क्रिएट कर दिए बट पार्टाइट के अंदर एज है कि नहीं ये भी तुम्हें प्रूफ करना है कि वो पार्टाइट के अंदर कोई एज नहीं होगा, तभी ये बाइपार्टाइट ग्राफ हो सकता है। सो टू प्रूव दैट देयर कैनॉट बी एनी एज विद इन द पार्टाइट, यू प्रूव इट बाय कॉन्ट्राडिक्शन। You say that suppose there is an edge, between AC. Now it claims that if there is an edge AC, then there is an odd cycle. But you start that the graph G doesn't have an odd cycle, and if there is an edge here, then it always creates an odd cycle. That means this edge cannot exist. It means each of this partite is by itself an independent set. That means the whole graph, whole XY bi graph is a bipartite graph. Okay, so with this I conclude today's lecture, and I will send you the slide. And thank you.
Thank you.